Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers, because once we do, we'll be able to put a donate button, and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD, and working on a product to help people overcome these problems, because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Peter Vikesland. He's a Nick Perlman Professor and Associate Department Head at Virginia Tech. We're going to talk about monitoring drinking water using nanomaterials and very small sensors. So this should be a very interesting call. So Peter, thanks for coming.
Oh, my pleasure.
If you were, let's start out. Tell me about your background, and then we'll go into the current work you're doing in research.
Okay. So by training, I'm a environmental chemist. So I got my undergraduate degree in chemistry from Grinnell College in central Iowa. And then I got a PhD at the University of Iowa looking at drinking water treatment chemistry. And then after that, I essentially moved to the East Coast and have been here ever since. First in Baltimore as a postdoc at Johns Hopkins, and then for the last 20 plus years at Virginia Tech. Through all of that, I've kind of moved from drinking water treatment to subsurface contaminant remediation to back to drinking water treatment. So that's kind of the background.
Okay. How complicated, maybe it's laughable, but how complicated is the chemistry of drinking water, for instance? What are some of the main components and elements that make it healthy, unhealthy, tasty, not tasty, etc.?
So that's a loaded question there, but essentially the ionic constituents in water are what effectively make it so that you want to drink it or not. And then when it's treated, it's how much chlorine or other disinfectants that we use in this country. And so a lot of my work in the past was really looking at the chemistry of those disinfectants that are added. So how do we maintain them for a long period of time so that they can actually remove and inactivate the pathogenic organisms that we want to take care of, and not react with other things that might be present within the water. So really looking at kind of the details of how disinfectants are stable or not in water.
Where is the responsibility end for a municipality that sends me water? I mean, they got to make sure it meets spec, I guess, up until the time it leaves the plant, but, you know, it goes through pipes and et cetera, and it comes into my house, and I may have stuff that leaches out of my pipes, blah, 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 blah. Where does the responsibility end for the water provider? And where does it begin for, let's say, the homeowner or the consumer?
So that's a complicated question, but effectively the responsibility for the provider ends as soon as the water enters into your house. But there is a lot of different contaminants that the regulations vary depending on whether you're talking about something that's organic that might be formed in the water as it transits from the treatment plant to someone's house or a building or wherever the end use is. And then there's other things like lead and copper that essentially can form within the water as it moves through the system. I shouldn't say form, but be picked up in the water as it moves through the system due to corrosion. And so those are regulated a little bit differently than the organics.
So the water that you may work on or consult on, what is its source? Is it recycled? Is it from, virgin streams or anything? Like, I know you don't know for the whole country, but in the area you're in, where does the water come from?
So the water in Blacksburg, Virginia area essentially comes from the New River. So it's a surface water source that is fairly clean because it is primarily moving through a little bit of farmland, but a lot of mountainous terrain. So it's a moderately impacted surface water source.
Okay, what any contaminants that are new or increasing in the past 20 years? Microplastics, remnants of industrial pollution. I mean, commercial pollution, people dumping into the river. Is any part of it recycled, or is it again all new from the river?
I mean, there's new contaminants that have arisen over the last 20 years. I mean, one of the things people talk about are emerging contaminants, and essentially there's always something new that's emerging. And it isn't so much that they are necessarily new, it's more that we have the capacity to detect them. And so we've gotten better and better with our analytical techniques, and we can now measure things at ridiculously low levels that we previously just didn't know that they were there. So some of the things that people have been very interested in for the last few years are the perfluorinated PFAS compounds. Microplastics, nanoplastics are fairly big these days. Some of the materials that come off of tires as they are abraded as they roll down the road. And then there's been, for probably the last 20 plus years, definite focus on looking for pharmaceuticals and other types of consumer use products that can end up in the water.
Okay, so you said now things are able to be detected at very low levels. So what are some of the previous metrics, and what are some of the current possibilities? Was it parts per million and now it's parts per trillion? Like, what are the levels?
Oh, it's gone from parts per million to parts per trillion to parts per, well, what's beyond parts per trillion? Oh, yeah. So, I mean, they get lower and lower in terms of the detection limits. And, I mean, with PFAS in particular, I'm by no means an expert in PFAS. I mean, the detection limits are required to meet some of the new regulations are at the exceptionally low level that in many cases it's very difficult to reach those using standard approaches that are accessible to most water facilities.
So you're doing some new kind of sensors or instrumentation to be able to detect things at low levels, or what's your current research about?
Yeah, so our research is really trying to focus on using nanomaterials as an alternative approach to detect a variety of different contaminants in water. And much of our work is focused on biological contaminants, so in particular bacteria and viruses that are pathogens. And what we do is effectively we take a nanoparticle and we make it such that it is going to be specific for a target. And that target might be SARS-CoV-2 in water. So that SARS-CoV-2 is the virus that causes COVID-19. Or it could be antibiotic-resistant bacteria strain that we want to detect. So we make particles that are specific for something that we want to detect. And then we use spectroscopic techniques. So essentially thinking about doing things where we see a color change that we can detect, typically not at the low levels that you might be able to do using the really large instrumentation that you find in the lab, but at things where we can scope a water to see if there is contamination, and if so, we can then send that sample on for further examination to really get at what the concentration is.
I guess ideally you'd have flow measurements. You don't have to pull out a sample. Like if you could do in situ flow measurement, that would probably be ideal. Maybe you could shoot lasers through the stream of water as it moves, or electrostatic precipitation, whatever it may be, and analyze it without stopping its flow, without having discrete samples. You could do maybe continuous sampling, moving averages, et cetera. Where is the instrumentation going? What does the ideal look like?
You hit the nail on the head right there, in that essentially, I mean, the ultimate goal for water sampling would be to collect things in real time as the water flows past and effectively be able to relay that information to the treatment plant, to the consumer potentially, to regulators and so on. We're not there yet. We can do those kinds of measurements for salts, for some other fairly simple kinds of things, but trying to do that for pathogens, trying to do that for organic chemicals of potential concern, we aren't there yet. Instead, what's typically done is you collect a sample. What we're trying to do is make it so that we can process them and analyze them in the field and have that information very quickly. But more typically is that you collect a sample, you bring it back to the lab, and you analyze it there.
Okay. So what are some of the analyses that you're doing that you're improving, either getting lower levels of detection or detection at lower levels, or again, experimentally being able to do it in a flow situation? Like, what's the focus of your research right now?
So the focus of our research of late really has been actually detecting SARS-CoV-2 in samples using a modified version of the lateral flow tests that we're all familiar with from doing nasal swabs in our homes to see if we're infectious or not. And so we've been taking that and trying to modify it so that it's a bit more sensitive, so we can detect SARS-CoV-2 virus down at a level that's about tenfold better than what we can do with the commercial tests. And we can do it on samples that have highly variable chemistry. So,
well, what's the point though? This is municipal water. I mean, what's the point of having virus, counts in there? I would think that just ultraviolet light, going over the water would kill a lot of that stuff. Or is it, if it has high turbidity, the virus just kind of cling to dirt particles? Or what's the reason for this?
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
So the reason for that particular study is a little bit less to do with water and more to do with thinking about indoor air quality. But the fundamentals are the same in that we've done this approach to try to make something field deployable. And we've done similar things, but not nearly to the same extent to detect antibiotic-resistant bacteria. And your point that things will stick to sediments and so on is true. But one of the questions is always how good are our treatment processes? And do we have breakthroughs? And we're just trying to develop approaches that will allow us to assess that.
Okay, so in addition to SARS-CoV-2, like what methods are you using to detect these things, and what other contaminants of concern are there besides this?
So we use a spectroscopic technique that's called surface-enhanced Raman spectroscopy, which is a really long name, but effectively what it is a laser-based method that essentially we use a laser to interact with these nanoparticles that we have produced that are specific for our target. And the target, again, could be SARS-CoV-2. It could be methicillin-resistant Staphylococcus aureus or MRSA. It could be atrazine if we're worried about levels of pesticides or other organic chemicals in the water. And essentially we take the sample, we mix our particles with it, and we use this laser to interrogate it. And then we collect a spectrum that says it's there or it's not. And again, the idea is to give us kind of field-based measurements of whether a contamination event has occurred or not.
So it's just a certain threshold, either below or above, there or not there, according to the test, or what?
To a great extent, yeah. I mean, essentially, we can get concentration information if we want, but oftentimes it's a lot easier to get a yes-no that tells us that we need to go back to the lab with the sample.
Instead of just saying yes, no to the presence, why not look at concentration? If it's going up, why? And that'll lead to an out-of-control event. If it's going down, why? Why not look at that data too?
Yeah, no, I mean, by all means, I didn't want to make it sound like we only are trying to do yes, no. It's more just trying to delineate between simple, which might be a yes, no answer, just to see if there is some level of detection, or being a bit more rigorous and trying to do concentration tests. So going back to this method with doing surface-enhanced Raman spectroscopy, which again is a nanotechnology-enabled approach, the idea is that we can do concentration. So the SARS-CoV-2 test that I mentioned, when we do like a lateral flow test like we buy at the pharmacy, that's just a yes-no. You might see that the color is a little darker, you might see that it's a little lighter, but it really isn't telling you anything about concentration. We can do that same thing, and we can actually determine concentration. So we do have that capacity. It's just oftentimes the yes-no is the simpler question and a lot easier and a little bit simpler in terms of the design.
Okay, so is this surface-enhanced Raman spectroscopy, what is it good for? What is it not good for? What kind of contaminants is it useful for, and why?
So we like the technique because it's very target agnostic. And what that means is essentially it often can be used for all kinds of different potential contaminants. So when you try to detect metals, when you try to detect bacteria, when you try to detect organic chemicals using existing approaches, you need a variety of different analytical methods. The nice thing about surface nanofilaments spectroscopy is when you can get it to work, that it actually has the capacity to detect metals, bacteria, organic chemicals all at the same time or in rapid sequence, because what you're looking at is the molecular vibrations in the target. So it's, again, an agnostic technique that is amenable to doing multiplex or multiple analyte detection in rapid succession.
But is this organic material or is it inorganic material? Like, what is its area of specialty and which types of contaminants is it not amenable to?
So it's really amenable to most everything that you can get to associate with the nanoparticles that are a key to making it work. And so, I mean, in our past studies, we've detected pesticides, we've detected pharmaceuticals, we've detected different strains of bacteria, we've detected a variety of different viruses. And it really is nice in that you can use this one tool and detect a variety of different things. We have to do some modifications and manipulations to shift from one thing to another, but it is still just the same instrument in the end.
Yeah, but are you relying on contaminants adhering to particles and that's what constitutes surface? Or are these free-floating contaminants that, you know, again, they're large enough still to be analyzed using this kind of spectroscopy? Or do you need more macro-sized, again, particles that act as like either nucleation sites or, you know, refuges or harbors for these kind of materials?
So what we rely on are particles that we engineer and design that are specific for what we want to detect. So you still have to get those particles to interact with what the target is. So in a water sample, that is arguably fairly straightforward. You just have to get that dissolved or particulate target to associate with these nanoparticles. And those particles can be in suspension, so entrained in the water, or they can be adhered to a solid surface. And we just have the analytes associate with that solid surface. So there's a variety of different ways that we can construct such a sensor.
Well, if you have ones that are free-floating in the water, I mean, then it would get into people that consume the water downstream. So it sounds like it'd be better to have fixed ones on a bed that the water, again, flows over and things would adhere, but it doesn't really affect the concentration of material in the water. Otherwise, like you said, people have to be able to ingest it in safe amounts and, you know, that it doesn't affect them negatively. So what happens here?
So the way that we often do these tests is to collect a water sample. And so then this is a interaction occurs in a vial in the back of our car as we're doing the analysis. But again, thinking forward, I mean, if we do want to have inline detection and we kind of implement this for water that flows past, then by all means, you would want to definitely think about having adhered particles so that you didn't have nanomaterials or other things being carried along and onto the consumer.
Okay, I see what you mean. So, I mean, what is the consequence of what you find? What do you find that requires action? Do you alert the municipality, or is this just, again, experimentation to see if you can detect stuff? Like, what is your interaction with actual water providers, or is it just more lab material?
So at the moment, most everything is lab material, but we're getting to the point now where the technologies are getting better and better, and the cost of the laser that is required to do this and the spectrophotometer continue to fall, that we're getting very close to being able to present this to municipalities, to water treatment facilities, to say, hey, we have this technique and we'd like to think about using it, and then kind of trying to build that kind of those connections. But I don't know that there's anybody in the country or even in the world that is actually doing these kinds of methods in the field with actual practitioners.
Okay, so are there particular bodies of water that you have like a long longitudinal view of what's going on with them? Are you sampling on a regular basis for the same things and, you know, seeing the different levels? Or is it just when the incident occurs? Like what's the goal of this monitoring?
I mean, ultimately, it is to have long-term monitoring of a particular body of water, a particular water distribution network, a sewer network, all of the above. So it's really trying to think forward to being able to develop a sensor network effectively that can tell us information about what's happening in whatever the water body is that we're interested in.
Okay. So what are you trying to do going into the future here? Again, is it you're going to have a SARS-CoV-2 monitoring program for various water sources, or, what in the research is your main goal right here?
I mean, short term, the main research goal is to develop these kinds of sensors and the sensor networks for particularly detection of antibiotic-resistant bacteria and the antibiotic resistance genes that they carry. So that's a long-standing focus, kind of that's been in parallel to our work with nanosensors. And so we've been doing metagenomic sampling or metagenomic analyses of waters across the U.S., waters across the world, and we want to continue to do that, but apply our nanosensor technologies to do that.
Okay, well, very good. What's the best way for people to find out more about your research and your work? Where can they go?
I think the quickest place would be to go to the Virginia Tech webpage and find my own personal webpage.
Okay, last name is Vikesland.
That's correct.
Okay. All right, great. Well, Peter, thank you so much for coming on the podcast. I appreciate it.
Thank you. You have a good day.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.